So we're used to rectangular coordinates with x and y values. We're going to be talking about polar coordinates, and these have r and theta. So this is just an alternate way to give someone directions to a particular point on the plane. Instead of telling someone how far to go left and right and then how far to go up and down, we're going to tell them which direction to point in. That would be the theta. And how far to walk. That would be the r. You're going to find lots of connections with this and vectors. So our main goals for today are going to be, if I give you coordinates of a point in x, y, can you turn them into polar coordinates, r theta? And then vice versa, if I give you r theta, can you turn them into x, y? One of those things is significantly simpler than the other, but they're both things that you'll be just fine with. And then we also want to be comfortable converting equations from a y equals equation into an r equals equation, and I'll show you how to graph polar equations on your calculator. That's what we'll be messing around with next Wednesday. And that'll be it. Yeah, so this is still 2D math. We're still talking 2D math. We're just giving the position in a different way. So instead of me saying to get to this point right here, so this is my example point. If I wanted to give you directions in rectangular coordinates, I would say start at the origin, go positive 4 in the x direction, and then go positive 8 in the y direction, and you would think of that point as having the coordinates 4, 8. That is a viable way to give the coordinates to that point. But there's another way. Instead of that, I'm going to tell you stand at the origin and face in a particular direction. Okay, and that direction we're calling theta. Face in a particular direction and then walk forward a certain distance, and that will get you to that point. So that point 4, 8, when I tell you, find the point 4, 8 for me, you guys are all familiar with that because you've been dealing with Cartesian coordinates probably since elementary school, middle school at least. Right? But there's another way to give directions to a point, and we just want to get a little familiar with that. So r would be the distance from the origin to the point. And theta is going to be our angle, and of course theta is going to be in the same position, that standard position that we used for the unit circle, that we used for vectors. Does this kind of remind you of vectors a little bit? What would be the corollary for vectors? What would r be when we're talking about a vector? It'd be like the magnitude of the vector, right? So finding r is going to be just like finding the magnitude of a vector. It's the exact same equation. I'll put that up on the screen here in a second. And then finding theta, well, we've already found angles of vectors. This is the exact same thing. Yeah, question? It does stand for radius, yes. R is radius. Or radial distance. Same difference. All right, so instead of x and y, we've got r and theta. That's the big idea. Let's go ahead and find the polar coordinates for this thing. I'm going to show you the formulas in a minute, but I bet you guys are going to be able to find it without. R is going to be the length of this side right here. That would be the same as the magnitude of the vector 4, 8. Do you guys feel comfortable finding that? Go ahead and do it. I'll give you a hint if you're not sure. It's going to look something like this. That's how we found magnitude, right? 16 times 5. How'd you do? Did you get a magnitude? Theta is just going to be the angle of that thing. We've done theta before too, right? I'm going to go ahead and put my coordinates on here. This is 8 and this is 4. And we're just going to use tangent. We'll use tangent. Tangent is opposite over adjacent. I'm going to actually use inverse tangent. So I can put my fraction straight into it. Opposite over adjacent would be 8 over 4. And that's just going to go into my calculator. Let's use degrees for this one. I'm going to change my calculator into degree mode. $63-ish. What do you guys think? Is this mind-blowing? Or does this seem like something you're really familiar with that we're just sticking a different name onto? I hope so. So my R value is, the exact value would be 4 root 5. That's about 8.9. So again, I just want you to remind you what we're doing here. When we give these values, we're telling you, instead of telling you to go left or right and then up or down, I'm telling you, you're going to walk 8.9 feet. But before you walk 8.9 feet, you're going to turn so that you're facing the direction of 63.4. So imagine a person standing here, and they're facing towards, here's their shoulders and their head, bird's eye view, right? And they're facing towards a positive x-axis. They're going to turn 63.4 degrees so that they're facing this way now. And then they're just going to walk 8.9 feet, and they're going to land at that same spot. All right. Cool. Let's get some equations down. I bet some of these you're already going to know. Yes, you will need to know these, but I don't think... I think if you can make some connections to something you've already known, I believe you've probably already learned these equations, right? These are the same equations we used with vectors, right? We did the magnitude times the cosine of the angle and the magnitude times the sine of the angle. So if you can connect r to the magnitude for the vector, you've already got these down. R squared equals x squared plus y squared. That's just the Pythagorean theorem. That next one's kind of interesting. That's like the magnitude, but there's a plus or minus in front of it this time. We'll talk about negative values for r in a moment. And then this last equation is always true, but you got to be careful about your quadrant, because sometimes when you're solving for theta, you're going to get a reference angle, but that's not your standard position angle. And we've dealt with that so many times at this point. I don't think that's going to throw you for a loop. Give you a second to get those down. Dun, 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 dun. Dun, 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 dun. Let me use this guy. All right, so R is allowed to be positive or negative. What would it mean if R was negative? Yeah. So here's my little guy. We're going to use, he's a little froggy. So here's my little guy. If I want to give him these directions, he's facing towards the positive x-axis. We tell him, turn so you're facing 63.4 and take 9 hops ahead. And that gets him to that spot, right? But there's a way we could tell him to do this with a negative 9-ish instead of a positive 9-ish. What do you think it means if we say negative 9? He's going to hop backwards, right? So we would have to find a different angle if we wanted to get him to that spot. We're going to have him face the opposite direction and then hop backwards to get to that. So how much are we going to have to add or subtract from our angle to get him to face the opposite direction? 180. And then, is anybody going to be surprised if I tell you that this is not the only angle that will get you to that point? 63.4. What could I do to 63.4? I could add 360 to that, right? Here's my froggy facing at 63.4. He can spin all the way around 360 and he's still facing that same direction, right? So there are lots of different correct polar coordinates for any given rectangular. So we'll practice doing a little bit of conversion now. Does anybody have any questions before we do that? Let's start with kind of the simpler way. If you do not have your unit circle memorized, this would probably be a good time to get that pink sheet out. So let's start with converting from polar to rectangular. This is the more straightforward version. When I give you something in polar, when you see a degree here, you see something with a pi in it, you can assume that I'm giving you r and theta. And they'll usually tell you that in the instructions. I'll definitely tell you that in the instructions on our test. Before we go on to this, I challenge you to write me another version of this same point. Let's keep the 10 as it is. We're moving forward 10. What would be another angle that would point us in the same direction as negative 210 degrees? You got me one? 150. What did you do to negative 210 to come up with 150? We just added 360. We've been dealing with those coterminal angles since like January, right? So we could use 150, and in fact, I'm going to use 150 because that's on my unit circle. I've got that memorized. So how do we find the x and the y coordinates? Well, my x is going to be r cosine theta. I don't know why I wrote 10. It's a deconstructed theta. R cosine theta, which is 10 times the cosine of 150, which is 10 times, what is the cosine of 150? Let's see here, it's going to be negative, and it's the bigger of the two. Negative root 3 over 2 sound right? And then we can simplify that. 10 times something over 2 is just going to be 5 times that thing. So negative 5 root 3 for my x coordinate. What if you just put this in here? That would be correct. It wouldn't be simplified. So on the test, the instructions will say simplify and give exact values if possible. Now, if this hadn't been negative 210, if it had been like negative 211, well, we don't have exact values for that, right? That would make this 149, and 149 is not on our sheet. So in that case, you could either give the exact value like you just said, or you could type it in your calculator and get a decimal approximation. In those instructions, that'll be clear to you on the test. If it's not, ask me. Yes, question? Okay. Let's find our y coordinate. Same deal, except it's sine this time, r sine theta. So 10 sine 150. Sine of 150 would be positive. That's in quadrant 2. That's this shorter distance. That's a half. That's it. Yeah. So r cosine theta, r sine theta. And if you think back to vectors, remember when I was giving you vectors, it was like Monday of last week, there was a sheet that had 6 problems on the front of it. You guys remember that? And each of the vectors had an angle and a magnitude. And this is exactly how you found your x component and your y component. You multiply the magnitude times the cosine of the angle and the magnitude times the sine of the angle. So you can make that connection. This is nothing new. All right, let's try this one. Oh, radians. Woohoo. That's our last memorization quiz, by the way, and that's next Friday. And it'll be all the way around the circle in radians. I challenge you to find me, before we get started, can you find me another version of this same point that has a positive 5 for the r value? What are we going to add on to 7 pi over 4? We'll add 2 pi, or 4 pi, or 6 pi, 42 pi, 64 pi. I'm going to go for 2 pi. 2 pi would be, let's see, over 4. That would be 8 pi over 4. 8 pi over 4 plus 7 pi over 4. I believe that would be 15 pi over 4. All right, let's go ahead and do this. So our x coordinate is going to be r times the cosine of theta, so 5 times the cosine of 7 pi over 4. 5 times cosine 7 pi over 4. 7 pi over 4 is in quadrant 4, so cosine's positive. And that's that multiple of 45 degrees, so they're all root 2 over 2's. Positive root 2 over 2. So that gets me 5 root 2 over 2. And y is the same thing except sine. Quadrant 4 sine is negative. How are we feeling? All right. That's it. That's it. All right, let's see if we can go the other way. Any questions on A or B here before we switch it up? We're going to go rectangular to polar next. Do I want you to multiply what now? So if I ask for a decimal approximation, we'd stick that in the calculator and get a decimal answer. I honestly don't know. I'd have to look. Yeah, I'll specify. I'll either say exact values. This is the exact value. It'll say, and if it's exact values, I'll expect it to be rationalized and simplified and all that fun stuff. Or a decimal approximation. Yep. And if I say decimal approximation, I'll tell you to round to the nearest tenth or the nearest hundredth. All right, let's do a couple of these. I'm going to save some space underneath this because once I find my polar coordinates, we're going to try and write some alternate forms. So I'm going to leave some space underneath this guy because we're going to write some alternate forms once we find it. So we're going to need two pieces. We need an r and we need a theta. So I'm going to focus on the r part first. That's easy. That'd be the radius. It'd be just like finding the magnitude if this were a vector. Do you guys feel comfortable doing that? Yes, we've done this a million times. Negative 2 squared plus 1 squared is root 5. And we need a theta. How are we going to find theta? Inverse tangent. Do you think we should sketch it, make sure we got it in the right quadrant so we know whether to add or subtract from 180 or 360? Maybe. Did you find that helpful when you were finding angles for vectors? I find it helpful. I would not just type in inverse tangent of this thing because, well, I'll tell you, you're not going to get a correct answer. You could do the inverse tangent of 1 over negative 2, and that will not be your correct. It will not be your correct angle. Okay? Because how do I know? What quadrant is this point in? Second quadrant. Inverse tangent will never give you an angle in the second quadrant. Yeah. So my recommendation is, just like every other time we found an angle this semester, just make yourself a sketch. Just a quick sketch. Sketch your little reference triangle. This point's going to be over here someplace. I'm not even using my tick marks or anything. This is just a rough sketch. Here's my reference triangle. My x coordinate is negative 2, so the bottom will be 2. My y coordinate is 1. The side would be 1. And we can use an inverse tangent. Inverse tangent is going to get us this angle if I use positive 1 and positive 2. But that's not the angle I want. That's okay, though. It'll be really simple for us to find the angle we want. We'll just find this and subtract it from 180. So this angle right here is the inverse tangent of, what would it be? 2 over 1 or 1 over 2? 1 over 2. Which is about, I think we just, no we didn't. 26.6-ish. But that's not the angle we want. We want to do 180 minus that to get our angle in standard position. Which is about 153.4. Let's just call that 153 for simplicity. All right, I've told you this a few times. There are multiple ways to find the angle of vectors and the angle for polar coordinates. So the way I fall back on is making those reference triangles because we've been doing it for so long. It should be kind of burned into our memory. If you're interested in other ways, there are some formulas out there. And I can point you in the right direction, but this works pretty well for me. Are you guys satisfied with just the little quick reference triangle? All right. Let's see if we can find some other versions of this. I would like a version where r is negative. So remember, this time my froggy needs to be facing away from the point because he's going to walk backwards instead of towards it. So he's facing the opposite direction from there. And he's going to walk backwards to that point. So what direction is he facing right now? He's not facing 153. What am I going to add or subtract from 153 to find it? We could add 180. If you're looking for the opposite direction, we could just add 180 to it. So I could do plus 180. I'm not trusting my mental math today. I don't know why. So 333 would get me an alternate version. What if I wanted a negative angle, a positive R value with a negative angle? I don't know why, but I just feel like it. Froggy doesn't want to turn to the left. He can only make right-hand turns. So how far does he need to turn to the right to get all the way around and be facing in the correct direction? So I would do I would take this and do minus 360. You could take this and do. Ooh, now we're getting complicated. I will go back to the original, right? Because this is the direction that we want to be facing, right? If I want another version of this, I would just add or subtract 360 from it. So I would go 153 minus 360, which is negative 207. If I wanted a negative R value and a negative angle, I could use the 333 and subtract 360 from that. And that would be 27, negative 27. And if I did everything right, these two things should be 180 degrees apart, and I believe they are. Okay, let's try this next one. Go ahead and find your magnitude, find your R, your radial distance. Ooh, weird. This one's interesting. Negative 1 squared plus negative root 3 squared. Huh. Yeah, I agree. Interesting. Interesting. Draw me a reference triangle. What quadrant's my point going to be in? Negative and negative, so fourth quadrant. Or third quadrant, thank you. Third quadrant. 1 and root 3. Oh, those numbers seem familiar to me. Oh, and the distance was 2 even? Oh, it's our old friend. That's a 30, 60, 90 triangle. Oh, the angle is going to be super easy for this one. What's my reference angle? Is it the 30 or the 60? It's the 60. Oh, cool. So then my angle all the way from the positive x-axis must be 180 plus that. 240 degrees. Hey. See if you can write me 3 more versions of that. Give me 2 versions where R is positive and 2 where it's negative. And then mix it up with some negative angles too, kind of like we just did. I'm sorry? Would it be what now? Over 360? The angle? No. If I did it over 360, then I would be finding like you could, if you divided it by 360, you'd be changing your units into revolutions, which we do sometimes measure angle in revolutions. Then we can multiply it by 2 pi and get radians. But no, I'd say let's just leave it in degrees. Now, on your assignment, there's a couple problems where they say give the answers between 0 and 4 pi. So I hope you will read between the lines and say, oh, they want radians and not degrees. Let's see here. All right, Froggy wants to face the opposite direction. So, oh yeah, for sure. So it's walking backwards to the point. So I need to go 180 off of that. 240 minus 180 would be 60 degrees. Now, Froggy wants to turn to the left to get there. It's going to go to the right. It's going to go negative 120. And if it's going to turn to the right and face the opposite direction, it's going to have to go all the way around 90, 180, 270, and another 30, 300. Is that right? Something seems wrong there. All right. We feeling all right? About to get in the complex part of the lesson. Yes. When the R is 2, that means the Froggy's walking forward. When it's negative, that means the Froggy's facing the opposite direction and he's walking backwards. Yep. So we did it for the negatives here. We said the Froggy could turn 60 degrees to the left. That would get him facing the opposite direction, and then he could walk backwards. Or he could turn to the right by 300 degrees, which would also get him facing backwards, and then he could walk back to it. Yeah. The negative here tells you whether he's walking forward or backwards. The sign here tells you whether he's walking forward or backwards. All right. Let's do some equations. So this will be a little bit trickier. We are going to convert equations. These are both rectangular equations. How do I know they're rectangular equations? Well, it says it on the page, but what kind of variables do you see in these equations? X's and Y's, those are rectangular coordinates. What are our polar coordinates? Theta and R. So we need to take these equations, we need to turn them into R and theta. So we had some formulas, some conversion equations that we're going to be falling back on. Let me see if I can get these on my screen at the same time. All right. So here we go. You guys ready? Let's do this. I'm going to change the format of this equation. I do not want a y in here. What could I substitute in place of the y? Y is not equal to theta. It's got a theta in it. I could substitute r sine theta in. Shh. Hey guys, come on. So I'm going to stick r sine theta in place of the y, and I've still got that 3 over there. And hey, look, no more x's or y's. Now, I will ask you to simplify if you can, which means, if possible, get r by itself. So we could divide by sine theta on both sides and get the equation r equals 3 over sine theta. I would like to show you how to graph this in your calculator. You'll be doing that in some of your assignments. So we need to stick our calculator into a new mode. We've been exploring parametric mode recently. The next one over from parametric is polar. I know, it's crazy. I don't actually know. I'm not sure. It's just sequences? So you get dots instead of... Okay. That's kind of boring. Polar is neat, though. Let's also go into radian mode. Radian mode and polar, and then go ahead and hit y equals, and oh my goodness, look, it's not y's and x's anymore, it's R1 and R2 and R3. Isn't that cool? So I'm going to type in my equation. It's 3 divided by sine theta. Where do you suppose I'm going to get theta? It's that button that we've been using for x and t. It says x and t and theta and n. That's our theta button also. Isn't that handy? Multi-purpose. And then before I hit graph, I don't know what my window's set up to, so I'll just go back to my standard zoom. So zoom, hit the zoom button and go standard, zoom 6. And look at that. It's a line. That's kind of boring. Does it match what we would have expected it to look like in rectangular form? Y equals 3 would be a horizontal line, right? So we can graph horizontal lines in R and theta. It's just we need sines and cosines to do that. Do you guys want to see some other interesting graphs? Yes, we'd love to. Okay, go back to your R equals. And let's do, let's go 0.1 theta. Graph that one. R equals 0.1 theta. Oh, that's not very interesting. It's tiny. Wait. Go to your window, and change your theta max to, I don't know, 20. Change your theta max to 20. Or something bigger if you want. There we go. Now it's more interesting. Oh, that's not enough. You said 360? Go back and change your theta max to 360. Now it's cool. Look at that. It's mesmerizing. Do you guys remember, if you get sick of watching this graph, do you remember how to make it stop? Hit the on button. Because you're probably in degree mode still. Those are pretty neat. We're actually going to explore a bunch of different types of polar graphs on Wednesday next week. This is a spiral. You see the little line going here in the corner? That tells you the calculator is still trying to graph. It's just not showing up on the screen. Remember, to interrupt it, you just hit the on button. All right, let's do another one. You're going to love this one. I don't know if I will. Y'all sure you will. I like this one. All right, write this down, please. And we did not spend a lot of time with conic sections in this class. I don't think you guys saw it at all last year either. Well, you did parabolas, but I don't think you guys graphed ellipses and hyperbolas, did you, last year in Algebra 2? Yeah, you might need to... That might be one of those self-study things next year. But anyways, I would like you to know that this equation, this format of an equation, is a circle. I would just like you to know this. This is for your own good. You're going to run into these in calc next year. That's a circle. How do I know it's a circle? Because it's got an x squared and a y squared being added together, and it's equal to some constant. I can tell you that this circle has a center at... Anybody want to guess what the coordinates of the center are? Close. Switch the signs. -1, 3 would be our center. Remember how... Yeah, remember like with parabolas when we were finding the vertex? Yeah, so it's the zeros of these two things. And this number here determines the radius, but it's not 9. The radius would be 3. It's the square root of whatever that number is. So this is the equation of a circle with a center at -1, 3 and a radius of 3. We're going to find a polar version of this equation. And we want this to be as simple as possible. So I'm going to give you guys a big hint here. We're going to go ahead and multiply out our two binomials. Let's use our shortcuts. Guys, we need to boogie here, so let's focus and get this going. Let's use our shortcuts. Squaring that binomial gets us x squared plus 2x plus 1. You guys should know these shortcuts at this point. Squaring this gets us y squared minus 6y plus 9. And then I'm going to do a little bit of rearranging here. First of all, I'm going to notice that we can subtract 9 from both sides, and those 9s are gone. Let me rearrange this a bit for you. X squared plus y squared plus 2x minus 6, that's supposed to be a y. And then we got a plus 1, and I'll leave the 0 over here. Why did I rearrange it that way? If you look at the beginning of your notes, we've got an equation for x squared plus y squared. What is x squared plus y squared equal to? Yes, it is a Pythagorean theorem. It would be c squared, but in our situation, that is r squared. X squared plus y squared equals r squared. It's in your conversions here. X squared plus y squared is r squared. 2x, that's just 2 times r cosine theta. And negative 6y, that's just negative 6 times r sine theta. And if we could, we would try and get r by itself, but since there are r squareds and r's, that's not going to be feasible. So we'll leave it like that. What did we just do? You tell me. We made an equation. Yeah, it's that same, it's going to be the same shape. Remember a moment ago we made an equation in r theta that had the same shape as this. That's what we just did. So this would also be a circle. If there was a way to graph this, we can't actually graph this with our calculators. So you could probably plug it into Desmos and it would graph it. Okay, why do we do it? Because sometimes it's convenient to have an equation in r theta instead of xy. You can't put it into our calculator because our calculator will only take equations that say r equals and then something without r in it. There's no way to get r by itself in this equation. All right, let's keep going. 2 more. Nah, maybe not. I've seen it do some. No, okay. Oh, I like what you're thinking. R equals 5 times the cosecant of theta. We're going to change this into rectangular form. That's in polar form. We're going to change it into rectangular form. And I'm hearing some good suggestions. Cosecant is the same as 1 over sine. You know, it'd be really convenient is if that sine theta was being multiplied by an r, because r sine theta is y. If we could make that sine being multiplied by an r, then that would be r sine theta. We could just change it into a y. Yeah, there's several things that we could do. I'm thinking just let's clear the fractions. Let's multiply by sine theta on both sides, and then over here we would have r sine theta. And then the sine thetas would cancel here, and this would just be a 5. So my step here that I didn't show is I'm multiplying by sine theta on both sides. Why do we do that? Well, because I wanted an r in front of my sine theta. Because r sine theta is y. And now I'm done. So y equals 5. This is my last one for you guys, and it's my favorite. And just ignore this right now. I don't want you writing that down because we're about to do it in a second anyways. R equals 2 cosine theta plus 6 sine theta. Once again, it would be really convenient if that sine and that cosine had a r being multiplied by them. Then we could change it into x's and y's. Also, I'm not a big fan of this r being over here by itself. Either this wants to have a cosine or a sine, or if we could make this into an r squared, that would be convenient. Because r squared is x squared plus y squared. Can you think of a way that we can deal with our issues here, with our problems? We multiply both sides by r, what's that going to get us? That'll get us an r squared here. That's good. And then we would end up with r cosine and r sine here. Oh, yeah, that's it. That's great. What a great idea. We're going to multiply times r over here. Well, we'll just multiply the whole equation times r. That's going to get us r squared equals 2r cosine theta plus 6r sine theta. Now that's convenient because r squared is x squared plus y squared. And r cosine is x, and r sine is y. Now that right there is going to get you most of the points on this problem on the test. There's going to be one just like this on the test. Would you like to see how to get the rest of them? Yeah. Yep. All right, let me show you. We're not done yet. That's my next step. We got a couple more steps to do. So I'm going to 0 on one side. That's all I did there. And I rearranged it to group my x's and y's together. You guys following that? All right, check this out. Where are we going with this? Yeah, good for you. We're going to complete the square. To get it into the format I need it in, yeah. Well, this is a great time to remind you of how to complete the square. It's not difficult. You take that middle term, you cut it in half, divide by 2, get you -1, and then you square it. -1 squared is just 1. You okay? Everybody good? Do the same thing here. Take the middle term, -6, cut it in half, gets you what? Cut it in half gets you -3, square it gets you 9. Now I just added a 1 and a 9 on this side. I need to add a 1 and a 9 over here. You're going to want to write this down, okay? You need this practice because it's going to come up again. And then, this will be our last step here. We can factor these things because they are now perfect squares. This is x minus 1, and this is y minus 3. And that's it. All right, so on the test, the final question will be, what shape is this? Where's the center? 1 comma 3, and what is the radius? Square root of 10. Oh, it's not too many steps. That's like 1, 2. I wouldn't even write this step down. I would jump straight to this. 3, 4 steps. You can do that. You can do that. I believe in you. Why is it the square root of this? So, like, I want you to think Pythagorean theorem. A squared plus B squared equals C squared, right? Yeah. And this is fixed, so that's going to get us that constant. Yep. Yeah. Good old Pythagoras. Yeah. All right, that's it. You guys did awesome. We're going to practice this. Next week we'll be reviewing, and then we'll be playing with some fun polar graphs, some limesons and lemniscates, cardioids with inner loops, dimpled limesons. It's going to be awesome. You'll love it.